Hi everyone, I'm Chromecat, and today we're going to be making this. It's a 3D engine from scratch, in Scratch. This is the first part of a 3-part series that I'm making, and the next 35 minutes you'll learn how a 3D engine is structured, how to store vertices and triangles in lists, and how to do screen projection and rotation matrices. Of course, 3D engine is pretty advanced for Scratch, but I'm going to try my best to explain everything clearly. Alright, so I've got here a blank project, and the first thing we're going to do is just delete Scratchcat. Then we'll create 4 sprites. The first one we'll just call Manager. Then we'll create a sprite called Setup, and a sprite called Render, and finally a sprite called Controls. Now you don't have to do this, but to make it easier to follow along, I'm going to put some icons into each of these sprites. And now what I'm going to do is just hide them when we start so we don't see these icons. Okay, that's good. The manager sprite is responsible for triggering the setup script, render script, and control script, and it's our central control center for everything that goes on in the project. So we say when green flag is clicked, broadcast, and then we're going to create a message setup. And then we'll say in setup, when I receive setup, and then we'll do something. For now, just setup, and we'll put run without screen refresh. And then we'll say broadcast, and we'll say start. And that's going to take us back to manager, where we'll say when I receive start, and then what we're going to do is begin the tick loop, which is a run without screen refresh, which is called every frame. And what it's going to do is trigger the render and then the controls. Great. And over here, we'll also do when I receive, I'll do render, then we'll do the same thing in controls. When I receive controls. Great. So that's the basic structure of most 3D engines. So we're now ready to begin the setup, where what we're going to try and do is create the data for a single vertex, which we're going to project onto the screen and then render it. And that's the most basic 3D thing you can do. So then in setup, we're going to create our first list, and it's going to be called Vertex World. And this is going to store all the vertices in our project. Now we're working in 3D, so our vertices will have an X, Y, and a Z component. So let's create Vertex World X. Then we'll create Vertex World Y. And then finally, Vertex World Z. Before we add any data, we need to reset. So we delete all Vertex World X, then we delete all Vertex World Y, and then we delete all Vertex World Z. And then we can add a single point. And because we're going to be adding lots of points later, let's make a custom block for this so we can reuse it. So make a custom block, vertex world.add, and it'll take an X, a Y, and a Z. So all we do in this custom block is we add the X to vertex world X, we add the Y to vertex world Y, and we add the Z to vertex world Z. And now we can just use that here, and we'll make a point just at 0, 0, 0. So that's the basic setup for a single vertex. Now we can render it. To render it to the screen, we need to do 2 things. One, we need to take the vertex and we need to project it onto the screen. And 2, we need to move our sprite to the projected location and then just put down the pen tool to draw a single dot. Now first off, because anything from a broadcast doesn't have run without screen refresh, we need to wrap everything in this. So we'll create a custom block render, which goes from the broadcast. Now we're going to create a block called view transform. And we're not calling it screen projection because later on we're going to be adding rotations. And so this block is going to hold both the screen projection and the rotation. So what even is a screen projection? Well, the idea is that if you have a 3D object and you want to render it on your 2D screen, you need to project those 3D vertices onto your 2D screen. And the way you do that is that you work out the intersection of a line which goes from the camera to the vertex with your 2D screen. If you're interested in the maths of how we derive screen projection, just pause here and you can see I've worked it out formally. It just involves similar triangles and the fact that corresponding side ratios are going to be the same for similar triangles. And then we do a simple rearranging step here. But honestly, I think it's just easier to understand that for 3D objects, at least with a perspective projection, the further away you go, the smaller that object is going to become and the closer to the center of the screen it is. So we just need to take the y or x coordinate and divide it by the z coordinate and then multiply by some constant. So all we have to do is take the vertex world x coordinate and then divide it by the vertex world z coordinate, just like that. And we can do the same for the vertex world y coordinate. And then we just multiply by some constant, and I like negative 300. We do that twice. And that's really all there is to screen projection. Now why negative 300? Well, if you see this diagram from before, there was a z near term, and that's the distance from the camera to the screen. And the distance from the camera to the screen is actually something around -1 to -2, and I like around -1.2, and all that affects is the field of view of your camera. And why negative? That's because we're using this OpenGL style right-handed coordinate system where the z-axis is actually the depth into the screen or out of the screen, with positive z being coming out of the screen. So if we imagine our camera was here, and we imagine our screen was here, then from there to there would actually be a negative distance. And then the reason why it's not just -1.2 is because we're actually going to multiply by half the screen width, because our initial coordinate system is in normalized coordinates, but we need it in screen space. So if we did something like -1.2 times 240, we'd get like -288, and then I'm just rounding to -300. So then all we need to do is loop through vertex world and then transform those coordinates into screen space. So we'll create two new lists, screen X and screen Y. And then we create a loop through vertex world, which requires an index variable I. We set I to 1, and then we just repeat for the length of vertex world X. We change I by 1. Then we add to screen X this new thing that we just created, and we add to screen Y this thing we created, and then we just need I. Now if we started here, nothing's going to show up on the screen because we aren't rendering anything. To render something, we're going to need the pen extension. So we can go here, then we can click pen. Then let's make another custom block for this rendering, which we'll actually call rasterize. So in our rasterize, we're going to loop over the screen coordinates we just created. So just like we did in view transform, we'll set I to 1, then we'll repeat for the length of screen X, change I by 1, and we'll just go to the item I of screen X and item I of screen Y. And then we just need a pen down here and a pen up here, and we'll set the pen size to something larger like 8 so that we can see it well. Then we just need to put view transform there and rasterize there, and we're good to go. So we start the project now, we can see there's a dot there, which is pretty good. But right now, we can't actually move. So to allow our camera to move, we're going to need to create 3 new global variables. It's going to be camx, and I like to put a little @ when I'm doing a global variable. And then we'll put cam y and cam z. And this is going to store the position of our camera. And now we can integrate the camera position into our view transform by just subtracting it during the screen projection. And the reason we subtract, not add the camera position, is because if you imagine we had a camera and that camera moved to the left, then from the camera's perspective, all the points would be moving to the right. If the camera moved to the right, all the points would move to the left. So we actually have to subtract the camera position. And now let's just show those variables. So in setup, we're going to set the initial camera position, and we're going to set it to 003, which we're going to do because we actually want our camera to start a little bit behind the world center, and that gives some space for seeing the model clearly. And then we just make sure that we are resetting the list screen X and screen Y if we're adding vertices to them. So delete all of screen X and delete all of screen Y. And just make sure that we are erasing the screen. And now we put a slider here. Okay, so it's moving a little bit fast, but you can see that it is moving. So the next thing we're going to do is make this controlled by the WSD keys. So we go over to controls. We have to create a new block called controls without screen refresh. I'm going to change camx by an amount that depends on the D and A key. So we want D to produce a +1 value, and we want A to be a -1. And a very simple way we can do that is with a subtraction of key D pressed by key A pressed. So D is going to be going right on the x-axis, and then key A is going to be going left. So we just multiply that by some small amount, or we'll go too fast, like 0.1. And we drag that in. Then we can duplicate that for cam Y. And this time we're going to be using the E and Q. And finally for Z, we're going to do the same. We're going to use W and S, but this time we're going to reverse it. So you'd think you'd use W to go forwards, but actually going to use S and W for going backwards. And that's again because of the positive Z that's been coming out of the screen. If we start our project, we can see that we can move forwards and backwards. But right now it's a little bit hard to see that this is in fact a 3D point. So what we need to do is add more points. And I think the best way to do that is to create a cube. So to create the cube, we're going to need 8 vertices, and I've got a useful diagram we can use. Here we go. So we're going to number our vertices in this particular way, which is going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we can do this in a very simple way. We'll just set this to -1, -1, -1. Then we duplicate it, and we flip this one to 1. Then we duplicate the whole thing, and we flip this one, the Y to 1. Then we duplicate it again, and we flip the Z to 1. And now if we run this, there we go. That's our first 3D cube thing. Those are the vertices. But wouldn't it be nice now if we had triangle edges? To do this, we're going to need to add a new data structure. It's called tries. And much like Vertex World, we'll have 3 lists, one for each of the vertices in a triangle. And what this is going to store is indices into Vertex World that define each triangular face of the cube. So we can create tries A, tries B, and tries C. Then we can create a new custom block called tries.add. And all that's going to do is add index A to tries A, add index B to tries B, and add index C to tries C. And then we'll create another custom block called tries.add quad, and this is going to be a shortcut for adding 2 triangles because we're going to need to do that 6 times for this cube. And what we'll do is just put 2 triangles, and the first one's going to go A, B, C, and the second one's going to go A, C, D. And we can see this from the diagram that effectively we're indexing this quad in a anti-clockwise order, which is pretty standard in 3D engines. And we're going A, B, C, and then we're going A, C, D. And now all we have to do is the fairly painful part of adding the 6 quads. And if we look at the costumes, they're going to be these ones, just defined by picking a face and then going anti-clockwise starting from the bottom left. This part's a bit tedious, but just bear with me. We can drag that on, and we just need to add one part. We need to delete all of tries A, otherwise this will just keep growing. And to make this a bit more organized, we'll just create a reset all block. Cool. Now in order to render this, we're going to change our rasterize to loop over the triangles instead of the vertices. So we'll do repeat length of tries A, and we'll be creating 3 variables to hold these indices, which is just going to be A, B, and C. And then we'll do set A to item I of tries A. And then we'll do set B to item I of tries B, and set C to item I of tries C. So remember, this is an index into the vertex list. So we need to replace I with our new index, just A and A. And then we can keep this pen down and copy this, and then we're going to, so let's say we just rendered this one, we're then going to render this one, then this one, and then back to that. So we'll do that with more go-tos. And now if we start that, there we go. So let's make this a little easier to see. So let's set the pen color to something like a bright red. Seems good. And then we'll have a change pen color, like 10. And let's decrease that pen size now that we're not doing dots. That's good. I like it. Okay. All right. So now we get to the fun part, which is we're going to make the cube rotate. And to do this, we're going to use a thing called rotation matrices. Now, rotation matrices are a bit complicated. If we go to the Wikipedia page, we'll get this wall of maths. And honestly, it's quite easy to get lost here. The problem is that you need this thing called linear algebra to understand rotation matrices. And linear algebra isn't even taught until first year of university. But I don't think that you really have to wait that long. I think that as long as you understand algebra and you understand trigonometry, the basics of linear algebra needed to understand rotation matrices is possible to understand. So with that in mind, I'm going to give my own simplified linear algebra math lesson. So the first thing we have to learn is what are vectors. Here is a 3-dimensional Euclidean vector, which stores an x, y, and z. you can represent it with an arrow like this, where if we have a vertex in a cube, for example, the vector is just the arrow going from the world center to that point. And then the next thing we need to learn about are matrices. A matrix is just concatenated vectors. In this case, we have a 3x3 matrix because it has 3 rows and 3 columns. Now moving on, we can learn about our first linear algebra operation, and it's called the dot product. Now a dot product is between 2 vectors, and all it does is take corresponding elements, multiply them together, then sum them up. So we can see here we have a1, a2, a3, and b1, b2, b3. Then the dot product of the two is a1 times b1 plus a2 times b2 plus a3 times b3. So now that we understand that, we can move on to the second big operation in linear algebra, which is matrix vector multiplication. To do matrix vector multiplication, you put a matrix on the left side and a vector on the right, and then you do the dot product with each row of the matrix. So you can see here that what we're doing is we take this first one and multiply it by this one, then the second one and multiply it by that, and then the third one and multiply by that. And that gives us this, and this is just, you can see, the dot product of this vector with this row. And we repeat that for each row, and that gives us the resulting elements of a new vector. Then the final operation we need to understand rotation matrices is the matrix-matrix multiplication. And really all a matrix-matrix multiplication is an extension of the matrix vector multiplication. So to get one column of the resulting matrix, you do a matrix vector multiplication, you get that column, and then you just move on to the next column and repeat it. And that's literally all there is. Okay, so that's our vectors and matrices crash course done. Now we can move on to rotations. So there's 3 types of rotations, yaw, pitch, and roll, and that just changes which axis we're rotating around. Now, yaw is around the y-axis, pitch is around the x-axis, and roll is around the z-axis. In our 3D engine, we're mainly going to care about yaw and pitch, because yaw is when our character looks to the left or to the right, and pitch is when they move their head up and down. Now the reason why we had to learn about these vectors and matrices is because it's actually possible to apply these rotations to the coordinates of our cube, or just really any object, with these matrices. So the way this works is that we're going to do a matrix vector multiplication with the coordinates, and if we multiply by these very specific sort of magic matrices, they will apply rotations, and this specific rotation depends on which one we pick, because this top one here, this is a yaw rotation matrix, and this one's a pitch rotation matrix, and this one is a roll rotation matrix. Now I get that the idea that multiplying a vector by a matrix does a rotation sounds a bit unintuitive, so I've actually put together an interactive demo which I think will help visually explain this. So here we have a unit vector, which means it has length 1, and in this case it's 2D, so it only has an x and a y component. And we're beginning with the vector 0.71 by 0.71, which is basically a perfect 45 degrees angle. Now over here, I have the 2D rotation matrix. You can see it's basically the top left part of the roll rotation matrix. And right now the angle is 0. But if I put in an angle here, you can see it's now rotating that vector around. And if I move the starting point, there we go, you can see that wherever I move the starting point, the resulting vector is moving. And here we can actually see matrix vector multiplication in practice. The resulting vector can be found by doing the dot product of this vector with this row to get that one, and then the dot product of the vector with this row to get this part. So it looks complicated, but it's actually quite simple. And the yaw, pitch, roll rotation matrices are doing exactly the same thing, except they're using 3D matrices and they're using a 3D vector. Now the very last thing we have to understand is how to combine these. We could just apply the rotation matrix to a vector, get the output, then apply the next one, get the output, apply the next one, get the output. But it turns out that if we use that thing we learned about before called matrix multiplication, we can actually combine all the rotation matrices into one mega matrix, which we do to save computation and make our 3D engine run faster. Now, I'm not going to go through the full matrix multiplication process live here, because if you remember what you had to do, it's actually going to take a long time. Just trust me that I've already worked this out, and that the resulting matrix that we need to use is this. So to make use of rotation matrices in our Scratch project, the first thing we have to do is build the rotation matrix. Coming back to render, we're going to build the rotation matrix at the start of view transform using whatever the current your pitch and roll angles are for the camera. Of course, we don't have your pitch and roll yet, so we need to make that. We have at cam your, at cam pitch, and at cam roll. Next, let's make a new custom block which is going to set that rotation matrix. It's called set rot matrix. Then let's tell people what our exact order of operations is. In this case, it's going to be roll, pitch, yaw, and rotation matrices are applied backwards. So we're going to be rotating the camera on the yaw axis, then the pitch axis, and then the roll axis. And our inputs to this custom block are going to be roll, pitch, and yaw, but we're actually going to pre-multiply them by cosine and sine, because we need to do that multiple times within the custom block. So if we do it once at the beginning in the actual custom block parameters, we end up saving a lot of computation. So let's make our first parameters be cosine of roll, then sine of roll, and then we'll do the same for pitch and yaw. So we can put the definition over here, and we can put the custom block here. Now we'll do cosine of at cam roll, then sine of at cam roll, and now we'll just repeat this for pitch and yaw. Now all we have to do is calculate each one of the cells in this matrix. Each value will be stored in a variable called rm for rotation matrix, and then a number which signifies the index into the rotation matrix. So we'll begin with rm1 and we'll continue to rm9. Now what I'm going to do is convert this rotation matrix into Scratch code. It's going to be a bit of pain, but don't worry, you only have to do it once. Just copy what I do. And there we go. That's the full rotation matrix setting custom block. I'm leaving it on the screen, just pause here and then copy that. And now we can use this rotation inside a matrix vector multiplication inside our view transform. And the vector we're going to be applying this matrix to is going to be the vertex world coordinate after the translation transformation. So this part. To make this next bit of code a bit more concise, let's create 3 temporary variables, x, y, and z, that store the vertex world coordinate after the translation transformation. X, y, and z. And then we do set x to this one, then set y to this one, and set z to this one. So let's create vertex x, y, and z lists. Now all we have to do is apply the rotation matrix to our x, y, and z vector, just like we saw here, which means that each element of the resulting vector will be the dot product of our x, y, and z vector with each row of the rotation matrix one by one. So we do add to vertex x, and then we set up the dot product, which has 3 additions, and inside each one of these inputs we have a multiplication. So let's copy that, and then we'll do multiply there and multiply there and multiply there, and then we just do x times rm1, then y times rm2, and then z times rm3. And now we can just repeat this exact same bit of code for vertex y and z, except instead of rm1, 2, and 3, we use 4, 5, and 6, and then 7, 8, 9. And now we can just replace the screen projection with our newly created vertex x, y, and z, where we'll just get the last items in the list. And we can do that by just doing item of our list, and then we need to basically just copy the word last from anywhere, and then just paste it in here, and this will get us the last item in that list. So we'll do that for the y as well, then for the z. Great, so believe it or not, we're actually done with the rotation part of view transform now. Let's just show the variables cam, yaw, pitch, and roll now. And if we start the project and we actually add a slider to this, there we go. We can now rotate the camera. We can do the same with pitch. And we can even do the same thing with roll. This is really my favorite part of the 3D engine, because who would have thought that such a random set of scratch operations would actually give us real 3D rotation? I mean, you've got to admit, that maths is pretty cool sometimes. So we're nearing the end of the tutorial now, and all we really have to do is hook up yaw and pitch to the left, right, and up and down arrow keys. So let's do change cam yaw by, and then we're going to do pretty much the same thing we did before. So we can duplicate that, but because our camera angle range is going to be 360, which is much bigger than the camera position range, we're not going to multiply by 0.1, but by something much bigger like 3. And then we'll use the same subtraction trick, but we'll do key right arrow pressed, subtracted by key left arrow pressed. So that means that when you click the right arrow, you're going to look to the right, and when you click the left arrow, you'll look to the left. And then we can just do the same thing, but for cam pitch, but we'll do key down arrow minus key up arrow. And you might think this is a mistake, and we should have done key up arrow minus key down. But just like with the Z, the weird thing we have with the Z axis means that we actually have to reverse these. So then we just drag this onto the rest of the controls, and if we start the project now, I can actually look around with the control keys. How cool is that? Okay, so the very last thing we have to do is in setup, just like we did with camera position, we need to reset the camera pitch roll in yaw when the green flag is clicked. And then let's also make sure in render to reset vertex X, Y, and Z, because we're adding points to that list. Alright guys, so that's all there is for this part of the tutorial, but in the next part we'll be learning about triangle filling and lighting so we can turn this from a wireframe cube into a proper filled in shaded cube. I think that's going to be really cool, so subscribe if you want to see that. But for now, keep on scratching.